Good morning. So here we are going to see about some more basic parameters related to the antenna characteristics. So this is beamwidth, that which is different from antenna bandwidth, where the antenna bandwidth, it is the ratio of the operating bandwidth or the absolute bandwidth divided by the resonant frequency, that is fH minus fL. It is absolute bandwidth divided by the resonant frequency, which is called as antenna bandwidth. And here beamwidth, it is the aperture angle from which the most of the power is radiated from the antenna, which is nothing but the beamwidth. So beamwidth can be defined as the area where most of the power is radiated, which is the peak power, right? So from at which angle we can get the maximum power radiation from the antenna, which is called as the beamwidth. There are two main characterization for this beamwidth. One is the half power beamwidth and the second one is the first null beamwidth. First one, half power beamwidth. Half power beamwidth, the angular separation in which the magnitude of the radiation decreases by 50% of the peak of the main wave is called as the half power beamwidth. So the half power beamwidth is the angle in which the relative power is more than 50% of the peak power in the effective radiated field of the antenna. Then next one, this is the pictorial representation of the antenna radiation pattern, which explains the difference between the half power beamwidth and the first null beamwidth. So this is the first null beamwidth. It is the angle of separation between the two adjacent side lobes, and half power beamwidth, it is the angle of difference at which the power is 50% of the maximum power, which is called as the half power beamwidth. So the first null beamwidth, the angular separation between the first pattern nulls adjacent to the main lobe is called as first null beamwidth. Next one, we can see the noise. So now there are the noise which can also be delivered to the input which is received by the antenna. So the input power received by the antenna can also contains a noise power. The noise power can be of two different source. One is the external environment and another one is the internally thermal generated noise. So the noise produced within the receiver, that is called as thermal noise, it can be controlled, but the noise received from the environment by the receiving antenna cannot be controlled, and it may exceed the noise power or the noise maximum level of the receiver itself. So there is important to characterize the noise power delivered by the received antenna. So here this is a simple example with the contribution of the resistor, where for the simple resistor, the output noise power N0 is equal to K T in B. K is a Boltzmann constant and T is the temperature and B is the system bandwidth. So this is a pictorial representation where we have the resistor at a temperature T and the antenna has been situated inside the anechoic chamber, and the antenna weaving the uniform sky background at a temperature T, and the same antenna has been projected to the sky also. So this diagram which explains the interference by the natural and man-made sources which will contribute to the background noise of the temperature. So what is background noise? It is an equivalent temperature of the resistor required to produce the same noise power as the actual environment seen by the antenna. So there are three typical background noise temperatures are 11 at low frequencies like sky and ground. So here we have seen when the beam of the antenna beam is very narrow, we can have the antenna background temperature. At the same time, when the antenna beamwidth is broad enough, the different part of the antenna pattern can be seen with respect to the background temperature, which is called as the effective brightness temperature seen by the antenna as the weightage of spatial distribution of the background temperature by the pattern function of the antenna, which is defined by this formula, which is the ratio of distribution of the background temperature to the directivity of the antenna. And here, so by knowing the brightness and the background temperature of the particular antenna, we can able to define the equivalent temperature of the antenna, which is represented by TA, which have the two component. One is with respect to brightness separator and the other one is with respect to the background temperature, which is defined by here the formula. TA is the antenna noise temperature, which is equal to antenna equivalent temperature, which is equal to the two component. One is by brightness temperature and the another one is the background temperature. Here in this case, when the when we have assumed that the antenna is lossless, in that case the radiation resistance, radiation efficiency is equal to 0, which is if you substitute eta radiation is equal to radiation resistance is 1. If you substitute eta radiation is equal to 1 here, this component will get cancelled. So the contribution for the antenna equivalent temperature is only because of the background temperature, so there is no brightness temperature. So if the radiation efficiency is 0, the antenna appears as a matched load and does not see any background noise, and then the equivalent and the equation reduces to the equivalent temperature Ta, which we having the only one component for this contribution, that is the antenna thermal noise generation, right? So this is the related to the difference between the radiation efficiency and the aperture efficiency. Here the radiation efficiency accounts for resistive loss, and the aperture efficiency resists to many different laws like reflectors, lenses and horns, and it involves the generation of thermal rush. Radiation efficiency is depending upon the thermal noise, and the aperture efficiency does not lead to any additional effect on the noise temperature. So the only contributed noise for the antenna temperature, antenna noise temperature is aperture radiation efficiency, not the aperture efficiency. So in next class we can see the more parameter about the characteristics of the antenna. Thank you.